Okay, so now we're on question 5. So the text before any of the parts of questions is imipramine, I think that's how you pronounce it, has been prescribed as an antidepressant. The structure of imipramine is shown below, and then they give us a structure. So thinking about what's useful, or what's likely to be useful, the name imipramine isn't useful at all. I mean, the amine part tells us an amine, but we can see that from the structure anyway. The fact it's prescribed as an antidepressant isn't useful, but the structure is clearly going to be useful, or is clearly going to be relevant. All right, so that structure is important, and we can already see that 2 of the nitrogens, or the 2 nitrogens, have been labelled A and B, so there's obviously going to be something referring to those 2 nitrogens. Okay, so then let's look at question A. So the medicine is usually applied as a salt. The salt is formed when 1 mole of imipramine reacts with 1 mole of hydrochloric acid. Suggests why the nitrogen atom labelled B is more likely to be protonated than the nitrogen atom labelled A when the salt is formed. Okay, so let's just make it clear where A is. Where A is. And let's just make it clear where B is. And we're talking about them being more likely to be protonated. So accepting a proton is the definition of a base. It has to have a lone pair. So we're just going to put a lone pair just to remind ourselves. And the fact that one is more likely to be protonated than the other, then we're considering, or what we're considering, is the availability of those lone pairs. So this refers to the area of the course where we made comparisons about the different basic strengths of the different amines, and also with ammonia. And it was all about the availability of the lone pair. So we don't even have to explain anything. The question, by telling us that one is more likely to be protonated than the other, then they're telling us that the lone pair on the nitrogen labelled B is more available. It's a conclusion from the fact it's more likely to be protonated, is more available. Oops. Than the lone pair on the nitrogen labelled A. Okay, now we have to explain it, all right? So now we have to give a reason for this. And if we think back to when we did the comparative basic strengths of amines, it was all about what groups were attached to the nitrogen. So they could be electron withdrawing groups, or they could be electron donating groups. So if we look at what's attached to nitrogen A, we've got 2 phenyl groups. So remember, directly attached. So what we're looking at is what is directly attached to the nitrogen. So 2 phenyl groups are directly attached. They are electron withdrawing groups. That's because the lone pair can become part of the delocalized ring, or can become delocalized into that ring of electrons in the benzene or phenyl group. So I'm just going to draw an arrow just to sort of visualize that. So electron density is being drawn away or withdrawn from the nitrogen. 2 phenyl groups. Then there is also an alkyl group. Alkyl groups are electron donating. So I'm going to draw an arrow towards. So we've got 2 arrows away, 1 arrow towards. We're making comparison. Remember, these are relative to each other, so that's why it's more likely. If we look at nitrogen B, we have 3 alkyl groups attached, so all of those are electron donating. So I'm going to push 3 arrows pushing towards the nitrogen. And really now these are our reasons. We just now need to put this into words. So now we're explaining why the lone pair on nitrogen labeled B is more available than the lone pair on the nitrogen labeled A. So I'm just going to make this, I'm going to move this up, sorry. So the lone pair on the nitrogen labeled A. So this is our reason for the first statement. Is delocalized. So this is it's important really when it's the phenyl group to not just say withdrawing, but to make it clear that the lone pair is delocalized or partially delocalized. But they're looking for the word delocalized into the benzene. Oh, there's actually two of them, so I guess we've got to put plural really. So we've got to focus on the key factors. Yes, there's also an alkyl group, but really, what is it that's going to make this different to B? It's the fact that we have those benzene rings directly attached to the nitrogen. Whereas, so this is 3 marks, so we'll come to that in a second. Whereas the alkyl groups attached to the nitrogen labeled B are electron donating, therefore increasing the electron density of its lone pair. There are slightly different ways we could have phrased all of this, but if we think about what's critical, availability, right? Making it clear that we're comparing the availability of the lone pair. That's 1 mark. Making it clear that with labeled A, the lone pair is delocalized into the ring. That's also important. And sorry, I'm just doing that, just sorting this out, sort my answer out. And then finally, making it sure that the alkyl groups are electron donating, so the electron donating bit, that they're alkyl groups, and that they are increasing the electron density of the lone pair. And that's our 3 marks. So that actually is quite a lot of writing for 3 marks, whereas quite often, sometimes 3 mark questions don't require as much writing as that. Let me know if you've got any queries about that. Okay. So, question 6. Okay, so the compound, and then it's CH3, CH2 twice NH. So let's write the name of that. That's diethylamine. So it can be made from ethene in a 3-step synthesis as shown below. Name the compound. Oh, so actually already done question A, so let's just do that then. So that's diethylamine. Okay, now I think sometimes you work forward, sometimes you work backwards. And actually we've got the 2 ends and we've got 2 things in between. Now, if we think about ethene, if we think about what it is, it's an alkene, right? And we think about the reactions that alkene took part in. They were electrophilic addition reactions. So let's consider that. So let's leave that for the moment, actually. But it's going to be electrophilic addition. If we look at the final thing, then we've got a secondary amine. And if we've made a secondary amine, then G has got to be a primary amine. Because if we've started with just ethene, we've started with CH2, sorry. We're going to make something with just 2 carbons, and then we're ending up with a nitrogen with 2 sets of 2 carbon alkyl chains attached to it. So I think that's got to be a secondary amine. So the G has got to be a primary amine. If we think about how we make a primary amine, we can make that from a nitrile group, from a nitrile, and we can make it from a haloalkane. If it was a nitrile, we would have 1 more carbon than our very starting product, which was ethene. But actually we can't make a nitrile from an alkene anyway. We can make a haloalkane, which is another way of making a primary amine. All right, so we've got to identify compounds F and G. So F is a haloalkane made from an alkene. It's got to be just a mono haloalkane. It doesn't matter which halogen it is. We normally answers will feature either bromine or chlorine. It's going to be chloroethane or bromoethane, so it doesn't matter which of those you put. And then haloalkanes undergo nucleophilic substitution. We're making a primary amine, so we're making ethylamine. And actually, when I wrote my primary amine there, it would have been a very fair assumption that it was going to have to be ethylamine, given that our final product was diethylamine. Okay, so for the reactions in steps 1, 2, and 3, give a reagent or reagents and name the mechanism. Okay, so give the reagent or reagents and name the mechanism. And this must be 6 marks because it's steps 1, 2, and 3. So it's really a reagent and reagents, 1 mark, and 6 marks. And then mechanism, the next one. All right, so step 1. So we go from an alkene to a haloalkane. That has got to be electrophilic addition. We've gone from ethene to chloroethene, or at least in my version, that's what I've done. So the reagent has to be HCl. Step 2. So we're going from a haloalkane to a primary amine. So haloalkanes undergo nucleophilic substitution. Okay, and then it must be ammonia. That must be our reagent because we are substituting a Cl for NH2. Ultimately. And then last but not least, we're going from a primary amine to a secondary amine. So actually what's happening is step 2 is being repeated. So in step 2, the nucleophile was ammonia. For step 3, the nucleophile must be G. So basically, this is an example where one of the problems, although this is obviously intentional here, but one of the problems of making an amine using haloalkanes is that you can get further or multiple substitution. So we're going to get nucleophilic substitution again. We know already that G is our ethylamine, so that means our other reagent must be our chloroethane again. So it's just about a question of perspective, really, in terms of... So the thing about synthesis, or the series of steps they give, they only focus on the things they want. That doesn't mean other reactions aren't taking place. So sometimes it's about perspective. So that's how we get the second ethyl group attached to the primary amine to become the secondary amine. Basically, there's further substitution, so that reaction, step 2 reaction, happens again, but with the amine as the nucleophile as opposed to ammonia. Okay, and then the final question, final part here, it says identify one organic impurity in the product of step 3 and give a reason for its formation. So we've already established that we can have multiple substitution, further substitution. That's how we were able to get the secondary amine. Further substitution could take place. So we could get the tertiary amine, we could get triethylamine. This could be produced, or even the quaternary ammonium salt. So either of those would be acceptable. And our justification for that is that further reaction will take place. Which is a key part of amines. If we wanted to minimize the chance of further reaction, so if we wanted to weight to favor just the primary amine being made, then when we use the ammonia in step 2, we would have had the ammonia in excess, and that would have weighted our product to much more just being the primary amine. If we wanted to certainly weight it towards the quaternary ammonium salt, then we would have had the haloalkane in excess. That would have encouraged further substitution. And that concludes that. So let me know if you've got any queries. Thank you.